moving on to the third problem, we have 35mm thick, two pieces of it were joined by a four 25mm diameter rivet, wherein we have an applied tensile force of 25 kilonewton at both ends. So basically, this will have a shearing effect on the cross-section of the rivet as well as the bearing effect on the contact between the rivet and the plate. So the unknowns are shearing stress for each rivet, bearing stress in each rivet, and the maximum average tensile stress in the plate. So now, each of the rivet are subjected to a loading. So what is the loading? Practically, in your higher subject like steel design, you will learn how to determine the force distribution on each of the rivet. So in this case, we have a uniform distribution wherein 125 will be just carried equally by the four rivets. So by that, we're gonna label the forces in each of those rivet equally divided. So meaning each of the rivet will carry certain loading. Okay. Okay, so it is assumed that 125 is equally divided for each of the rivets. So basically we have P over 4, P over 4 for that, P over 4, and of course P all over 4 for the last rivet. So if we know that one, we'll just have to apply the formula for the shearing stress. And the shearing stress is given by the formula tau is equal to the shear force all over the shear area. And then for the shear force, this is P over 4 for each of the rivet, 125. This is divided by 4. Okay. So of course we must have to multiply that by 1000 to make it in Newton unit. And then for the area, of course, the cross-sectional area, because as we can see, we have a cutting effect on this cross-sectional area. Okay. So we have here the area of the circle, 25 squared. So now we compute for the shear stress on each of the rivet. So we have here tau is equal to 63.66 megapascals. So that's for the shear stress at each of the rivets. So for the bearing stress, of course, there will be a contact now between the plate as well as the rivet if we apply the tensile force 125. So as we all know, we have the formula for that. So if this is the cross section, okay, there will be a contact area between the plate and the rivet. So here it is. This is the area, actually, contact area. Okay, so we know that this is the diameter and this is the thickness. So by that, we'll just have to apply this. Bearing stress is equal to the bearing force all over the bearing area. Okay, so simply we substitute. Of course, a rivet will absorb P over 4 again, on the bearing effect. Of course, this is 1000 to make it in newtons, and then for bearing area is diameter times thickness, and the diameter is equivalent to 25 times the thickness of 35. So finally, we have the bearing stress to be equal to, we have 35.71 mega Pascal. Okay, so I think we should correct this one value. This should be 125. Okay, 125 over 4. Okay, for the last unknown, the maximum average tensile stress in the plate. Of course, if we have a tensile load, there will be a tensile stress. So we all know that the tensile stress, the tensile area is the cross section itself. So the maximum occurs whenever this cross sectional area is reduced by the space of the hole. Okay, so meaning your area is no longer complete because there is a hole in it. So if we are going to have the cross section, say if we have this as the cross section, practically we have this cross section. Okay, so anywhere in this except for this section passing through a hole, meaning your cross section will be reduced. So if this is the cross section, okay, passing through that section, we'll be having a reduction or space here because of that rivet. So meaning the fiber that is being stretched is now reduced instead of a whole section. So here it is. This is the area now that is being stretched if we are going to deduct the hole in the rivet. Okay, so that's it, and then we'll just apply this simple formula. Sigma is equal to P over A. Okay, so when we have a tensile type of stress, of course this hole will have an effect on the fiber that is being stretched, right? But if we have a compression type of stress, whether this space is filled with the rivet, so meaning it has no effect on compression, or the space will have no effect on the compression. But when we have a pulling or stretching the fiber, of course the space would have a bearing on the area. So next we have to substitute now in this formula. Sigma is equal to P over E. Now sigma, or tensile stress, is equivalent to what is the force? 125 over 4 or 125? Of course, the force will be 125 because our force now is for the plate, not for the rivet. Okay, so we're going to adopt 125 here. We'll no longer divide it by 4 because again it is for this one or the plate. Okay, we still have to multiply that by 1000 to make it in newtons. And then for the area, so let us have the dimensions here. So we know that the thickness is equivalent to 35 millimeter. Okay, and we have also here the dimension. Okay, we all know that this is 100 millimeters. So practically that area is the net area. We'll just deduct the spaces or the hollow spaces there. So 100 by 35, we're gonna list, we have here 25 whole. Okay, this is 25. We have 2 of it, 25 by 35. Okay, so the tensile stress now will be equal to 71.43 megapascals. Okay, so that is for the maximum average. Why is it that the maximum? Because again, the area was reduced because of the spacing provided for the rivet. Okay, so it has a bearing on the tension, but with regards to compression type, it has no bearing. These spaces has no bearing. So that is the principle. So that's it for the problem number 3. Okay, so moving on to the fourth problem. The homogeneous bar supported by a pin at A is weighing 1,500 kilograms. It is resting on a frictionless vertical surface at B. Determine the smallest diameter of a bolt which can be used in shear stress to support A, which is limited to 80 megapascal. So if we look at the figure, so this bar is resting on the wall. At the same time, it is supported by a pin connection at A. And remember that at A, if we can see, practically there will be a double shear here. Why double shear? Because there will be a double cut action if this is being moved. If this rod is being moved. Okay, so what we do is just, of course, apply this formula. Tau is equal to V all over A. So what will be our shear force here? Of course, the computed reaction at A. So remember, there will be 2 reactions for a pin connection. Of course, we can obtain that by step-by-step analysis, wherein the first step is to establish the free body diagram. Say this is the rod. Let us now label its forces. On this wall, we have a perpendicular reaction to the wall. So whenever a certain body is resting on a certain flooring or a certain wall, the reaction is always perpendicular to the wall itself or the floor itself. No matter what is the inclination of this object, it is always perpendicular to it. So for example, this wall is a vertical one, therefore the reaction should be perpendicular, or it refers to the horizontal. Okay, so we have here the reaction at the wall B. perpendicular to the wall, and this one, the reaction at the pin support, we have a vertical, and we also have a horizontal reaction. So we have as well this one. What is this? The weight of the bar located at the centroid of the bar AB. Basically, we'll just have to obtain those values. Say I will label this as RA along X, and this is RA along Y. This is the weight. This is the reaction. Okay, so let us check the weight. Weight is 1,500 kilograms. Okay. This is 1,500 kilograms. Of course, we know that we should multiply it by the acceleration due to gravity to make it as a weight. Okay, so we have here 14,715 newtons. Okay, so our task is to get RAX and RAY so that it will act as the shear force on the support. Okay, so there will be this could result to RA with the RAX and RAY. Okay, so to do that, we're going to use the equilibrium equations first. We take summation moments at A in order to get RB here. Okay, taking moments at A, we have 14,715 times the moment arm, of course, that is half of 8, 4, and this has a clockwise rotation, so it is denoted by positive, and then RB would tend to rotate it counterclockwise, so that is negative. RB times the moment arm, we have here 7. Okay, 7. And then we equate it to 0. Okay, so therefore, the reaction at V is equal to 8,408.57. So this is in newtons. Alright? Okay, so looking at the free body diagram, it is obvious that RB is equal to RAX because they are only the one with a horizontal orientation. Okay, so we'll just have to equate RAX is equal to RB is equal to 8,408.57. Okay, so they have the same values for that. Okay, so we only have the other unknown RAY. Okay, so obviously, what is RAY? Again, there are only two vertical forces here that is counteracting each other. So therefore, by summation forces vertical is equal to 0, we can say that RAY is also the weight, 4,715 Newton. Okay. So now that we have RAX and RAY, therefore RA is the square root of RAX squared plus the vertical component squared. Okay, so we substitute 4,715. This is squared plus 8,408.57. This is also squared. We have an RA equivalent to 16,948.02 newtons. Okay, so again, RA will act as a shear at this particular joint, okay, because this has a double shear effect on the bolt. So our task is to determine the bolt if we have a limit 80 megapascals. Okay, going back to the formula. Okay, the tau is equal to V all over A. So we limit it to 80 and we just substitute the shear, computed shear, 0.02, and then the area is the area of the bolt. We do not know yet the diameter, so therefore diameter is equal to, so we have 16.42 millimeters for the required diameter at support A. Okay, so that's for problem number 4.